Alright, here's a standard CELO theorem exercise. So, just any group of order 216, I'm going to show that's not simple. So, the reason you should think to use the CELO theorems is that we know that all the CELO theorems in a group are conjugate. And so we can use that to help us identify potential normal subgroups. So, anyways, yeah, exactly. Okay, so, but first, we need to use a fact for this problem, which I'm going to go ahead and prove. So we need the following lemma. Suppose some group. Okay, fine. Suppose nope. That is not what I wanted to do. Let's go back. Suppose a finite simple group G X non-trivially on a finite set as X. I.e., there exists some X and X, and there exists some G and G, such that Gx is not equal to X. I guess I don't really need to write that out, but I did anyways. Then the result is that the size of G divides the size of X factorial, or you could say the size of X. So I'm just gonna say factorial. Okay. To prove this, see here. Note that. See here. So, what group action do we have? Note that our group action. Oh, yeah, just whatever happens to be the group action that we're considering. Note that our group action yields a homomorphism. We'll call it phi from G to the symmetric group on X. Yeah. Which you could also write as S sub the norm of X, which you can identify those with each other in the natural way. But, in any case, I'm just going to leave it at this, where phi of G equals sigma G satisfies. I'm writing the sigma G to specify that this is sigma G is permuting. So maybe it would be better to write. Would it be better to write the permutation group on X or the symmetric? I don't know what the actual what the right word to use here is, but it's all the same idea. What we're doing is you're just moving the elements of X around, and for permutations, we typically use sigma to denote those. So I'm just using a sigma here. So sigma G is so this is such that excuse me. For all X and X, sigma G of X is equal to G of X. Just the action of G on X. Kernels of group homomorphisms. Sure. I'll make that a little more legible. Are normal subgroups of whatever the original group is. So the kernel of phi is a normal sub. Triangles are hard to draw. This is normal in G. Since G is simple, curve phi is equal to E or G. What do we know about G? Let's see here. So if kernel of phi equals G, then phi of G is the identity map, or the identity permutation of X. I'm not sure if I'm using that right, but the identity action on X. That's for all G and G. And this implies for all X and X, and for all G and G, G of X is equal to X. Because that's what it means for G to be. Right, that's okay. So this should be sigma G. Sigma G of X equals, well, sigma G of X, which is equal to G of X, is equal to X. So there we go. Well, rather, sigma G of X is equal to X, i.e. You know what? Hold on. I think I'm not explaining this super well. I think what I need is some coffee. So I actually just brewed some coffee. So I'm going to get my coffee. And now I'm going to drink some coffee. And we'll see if this goes any more smoothly. Okay, so for all X and X and for all G and G, sigma G equals X, i.e. we can write G of X equals X. Right. Therefore, or rather I should say this contradicts, or, well, it's not contradicting because we're not doing a proof by contradiction here. I'm just going to say thus the kernel of phi is equal to G. Because what we're saying here is that if the kernel of phi, no. Kernel of phi is equal to E. Because if the kernel of phi was equal to G, then that would mean that G of X equals X for all G and for all X, which would, and so that would contradict this statement up here, that there is some X and some G such that Gx is not X. So, therefore, the kernel of phi is equal to E. So then, we know that, so phi is a group homomorphism, so if its kernel is trivial, then that means it's injective. Remember, that's because this is a group homomorphism. I had a Jacobson question a couple weeks back where I actually had to re-upload the answer because I forgot that fact does not hold if it's not a group homomorphism. If it's just a map and its kernel is trivial, then you don't know because there's no structure to carry that fact into injectivity. But anyway, so we know that phi is injective, and so we know that the image of phi is a subgroup of the symmetric group on X. Then by Lagrange's theorem, not Land, it's Lagrange, we know that the order of the image of phi divides the order of the symmetric group on X. i.e., so what's the image of phi? So you're the image of phi. Phi is this map that goes from G, or rather, what's the size of the image of G? So yeah, because so phi is injective. Wait, do we need injectivity? Right. Wait. Yes. Well, injectivity tells us that G is isomorphic to um there we go. G is isomorphic to its image. Because that holds whenever we have an injection. Because if you're injecting, then it's just, yeah. This, I wrote down in my proof that like this uses an isomorphism theorem, but then I was like, no, that doesn't use an isomorphism theorem. That's just a basic fact. But now I'm going back and thinking, because what you do is you have that diagram that goes from G and it goes down to G mod E, and you're mapping into this other thing, sim X, and then that has to factor through the quotient, but the quotient here is just G mod E, which is G. And so, um, and we know obviously it's going to be, right, okay, yeah, obviously. So it's surjective onto its image, and it's injective onto its image. You know what? We don't even need this. We don't even need to worry about is it this isomorphic thingy, because what we know is that obviously phi is injective and it's going to be surjective onto its image, and so phi is of bijection from G to the image of G. Phi is a bijection from G to the image of phi, and so they have the same size. And so we can just go ahead and replace the size of the image of phi with the size of G. And of course, the symmetric group on X, we know that the size of that group is is X factorial. And that is what we wanted to prove for this lemma. And now we can actually prove that finite group of order 2 6. Why does he even say a finite group of order 216? Can it just be like a group of order 216? Because if it's of order 216, then since 216 is less than infinity, that makes it finite. I don't know why this problem was written like that, but anyways, if we get through the rest of this quickly, then we don't have to worry about why this was written like this and anything like that. So, anyways, we're gonna prove the actual result. So now let G be a group of order 216, and if you factor that, that's 2 cubed times 3 cubed. Now by the Sylow theorems, we have N3. This is the number of 3 Sylow subgroups, i.e. the number of subgroups of G of order 3 cubed. But we know that this is equivalent to 1. That's not a capital Xi, that's equivalent to 1. That reminds me of, apparently there was this one mathematician giving a presentation. And apparently like if you look up the Greek letter capital Xi, it looks like this kind of. But this mathematician was giving this talk, and he wanted to, just as a joke, make the most confusing notation possible. And I think there was someone in the audience who would always like correct people's notation, or like say that they didn't like the notation. But anyways, like this guy just kept progressively throughout the talk using worse and worse notation, and eventually he wound up using xi divided by xi bar, and it's just, I don't know, I love that. So, anyways, by the Silo theorem, n3 is equivalent to 1 mod 3, and what else do we have? N3 divides, and I'm just gonna be super explicit here. It's the index of S and G, where S is some 3 Silo subgroup. And so we know that because these are all finite, we can actually do division here. And so this is going to be the order of G is 2 cubed times 3 cubed. And then the order of S is 3 cubed because it's a 3 Silo subgroup. But this, you just cancel out the 3 cubed and you just get 2 cubed, which is 8. So I guess you wouldn't remember this, like, no, this is not right. Yeah, okay, yeah, it is right, because n3 divides this whole thing. But anyways, so this thing here, you're not going to remember, oh, the index of this and this. All you're going to remember is like, oh, you take a look at the order of the group and you look at its factorization and you cross out everything that's related to this particular prime that we're considering. Or I guess it doesn't have to be prime, but whatever, like if this is n3, anything like 3 to the power of whatever, you just cross it out and everything that's left is what you put in here. So if n3 is equal to 1 mod 3 is equivalent to 1 mod 3, and n3 divides 8, so let's see here, n3, the first thing tells us that n3 could be 1, 4, 7, 11, and so on. It also has to divide 8, so it has to in particular be less than 8. So, or less than or equal to 8. And so our only options are 1 and 4. So thus n3 is either going to be 1 or it's going to be 4. And we're just going to break this up into cases and look at them both and see what happens in each case. If n3 equals 1, then if Q is the unique 3 Silo subgroup of G, unique because n3 is 1, so there's only one of them, then we know that the Silo, we know that the collection of Silo subgroups, like for any P, the collection of P Silo subgroups are conjugate, but here we only have one, and so if we look at GQG inverse, this is going to give us another 3 Silo subgroup, but there's only one option, so that's precisely Q. So for all G and G, GQG inverse is equal to Q. Which means, now what is this? What is this the condition for? Which means that Q is a non-trivial normal subgroup. Because this condition is just how we defined normality. So yeah, which means that Q is a non-trivial normal subgroup of G. And so G is not simple, because to be simple means that you have no non-trivial normal subgroups. And here we have a non-trivial normal subgroup. if instead n4 equals, no, n3 equals 4, then let Q1, Q2, Q3, Q4 be the 4 3 CeeLo. Come on. Didn't I'll erase that much. 3 CeeLo subgroups of G. We know by the CeeLo theorem that Gx here. I'm gonna use a cursive Q. What is cursive? Is it what? For it's like what does a cursive Q look like? There's like a thingy. It's like that sort of. You know what? Let's use cursive R because it's close to Q and I don't know how to draw a Q. Gx transitively on R, which is not Q, but which is something I can write. This is by conjugation. Because any two p CeeLo subgroups are conjugate, which means that the action on the collection of CeeLo subgroups by conjugation is transitive. So here, Gx transitively on R by conjugation. So let's see here. Okay, and so what is the Okay, so we have okay, so Gx transitively on R by conjugation. The norm of R. Okay, so we have G acting on R. The norm. Actually, no. Here's a great thing that we should use. We should call this X, because not only can I write that, but you're going to start to recognize this. So X factorial is 4 factorial, which is 2 squared times 3, and the norm of G is 2 cubed times 3 cubed, which does not divide 2 squared times 3. And so by our lemma, or rather by the contrapositive of our lemma, G is not simple. Because our lemma was that if G is simple and we have a transitive action of G on X, then we have this division of the norm of G dividing the norm of X factorial. But here we have G acting transitively on X, but this division not holding, and therefore G cannot be simple. So G is not simple regardless of the value. Or rather, I'm just going to say, so G is, maybe I should not be erasing a bunch at the end of the video when the computer's slowing down. But anyways, so G must be simple is the conclusion, because it's either n3 is going to be 1 or n3 is going to be 4. If n3 is 1, then G is simple. No, I'm sorry. If n3 is 1, then G is non-simple. Is not simple. If n3 is 4, then G is not simple. No, why did I write G must be? So G cannot be simple because either n3 is 1, which means it's not simple, or n3 is 4, which means it's not simple. And so, let's see here. The first part of this proof at the end, the thing where we had only one CeLO subgroup and concluding that, oh, this is we only have one CeLO subgroup and the CeLO subgroups are conjugate, and therefore this CeLO subgroup is a normal subgroup. This is a very common, very powerful tool in these types of problems. It's a very easy way to get normal subgroups, because if you're just given a group, there's no like magical way to be like, oh, obviously I can tell if there's a normal subgroup or not. But a lot of times, if the numbers work out for you, particularly using these two things, n3 is equivalent to 1, or np is equivalent to 1 mod p, and then np dividing all of the other factors that don't involve p. Those two things together, if they work out and they get you that np must be equivalent to 1, then np must be equal to 1, then you've automatically got a normal subgroup. And that's a powerful thing. But in this problem, we had more possibility. Well, we had another possibility. We had the possibility of n3 is equal to 4, and in that case, we had to just recall some general counting result from group actions. And so, yeah, there you go. This is kind of a nice, typical use of the CeLO theorems. Because the main things that seem to come into play when you do exercises involving CeLO theorems is you have to memorize these two formulas, or understand them well enough that they're basically memorized, or you can derive them. I don't know, but this np is equivalent to 1 mod p, and np divides the other factors. Those are very powerful tools, and those come up in almost every CeLO theorem problem. And then the other fact is the fact that the G acts transitively on the p CeLO subgroups by conjugation. That's also very powerful. So anyways, yeah, that's how you do these types of problems, and more specifically, this is how you do this problem. And we are done.